All right, welcome back. In our last explainer on half-life, we figured out how to predict what's left of something over time, but we left the biggest question on the table. Today, we're going to find the mathematical key to finally unlock it. So let's dive right in. Our half-life formula, it's awesome for finding the amount left after a certain amount of time has passed. But what if we need to do the opposite? I mean, how long until a radioactive spill is actually safe to be around? To figure that out, we need to solve for t, for time. And right now, it's kind of stuck. And here is the heart of the problem. In our formula, A equals P times 0.5 to the power of t over h, our t is trapped up there in the exponent. Your normal algebraic tools, division, subtraction, they can't get it out. We need a special key, a tool specifically designed to break into exponents and pull that variable out. And that key, my friends, is the logarithm. The easiest way to think about it is, it's just thinking in reverse. An exponent, like 2 to the power of 3, asks a question. What's the result? The answer, of course, is 8. A logarithm just flips that question around. Log base 2 of 8 asks, hey, what power do I need to raise 2 to in order to get 8? And the answer is 3. You see? It's a perfect inverse operation. So the most important takeaway is really simple. A logarithm is the tool we use to undo an exponent. It's exactly what we need to free our trapped t variable. Okay, so we know we need to use logarithms, but how do they actually help us? Well, there are a few rules for how they work, but the one we really need for our problem is the most useful one of all. It's called the power rule. And this, right here, is where the magic happens. The power rule tells us that if we take the log of a number that's raised to a power, we can just pull that power right out and move it to the front. See that? The x literally just pops out of the exponent and becomes a multiplier. It's not trapped anymore. This is exactly how we're going to rescue our t. This is such a great practical question. You're probably looking at your calculator right now and you see a log button, which is base 10, and an ln button, which is the natural log, or base e. But you're not seeing a log base 0.5 button anywhere. So are we stuck? No way. Math has a kind of universal adapter just for this situation. And here it is, the change of base formula. This little gem lets you convert any logarithm, no matter how weird the base, into a simple fraction using the log buttons you actually have on your calculator. So log base b of a just becomes log a divided by log b. It's that easy. Now, no logarithm can hide from us.
Okay, we've assembled our toolkit. We have logarithms, we have the power rule, and we have the change of base formula. It's time to put these tools to work and finally solve our half-life problem.
Let's just walk through this nice and easy, step by step. Okay, step 1, we start with our original equation. Nothing new there. Step 2, our first move is to get that part with the exponent all by itself. So we just divide both sides by p. Simple algebra. All right, step 3 is the big play. We use our key. We take the logarithm of both sides of the equation. Because what you do to one side, you have to do to the other. Now for step 4, the magic trick. We use that power rule we just learned. And look, that entire exponent, t over h, drops right down out of its prison and moves to the front. Our variable t is finally free. The rest is just cleaning up. In step 5, we do a little rearranging, multiply by h, divide by log of 0.5 to get t all by itself. And there you have it, a perfect formula to find the exact time. This quote from William Paul Thurston really nails what we just did. We didn't just shuffle some symbols around. We used a logical tool, the logarithm, to get a much deeper understanding of the relationship between time and radioactive decay. And now we can finally answer that critical question, how long will it take? So really, the key takeaway is this. Logarithms are the tool that unlocks answers trapped inside exponents. They can turn these really complicated exponential problems into much simpler algebra. We use this for radioactive decay, but think about it. This applies to compound interest, population growth, pretty much anything that grows or shrinks exponentially. So now that you can solve for time itself, what will you predict?